Hello, we, Trofimova Mariia and Arkhipov Mikhail, are presenting our paper, Transformer for Hypernym Extraction. This paper describes our solution as HyBERT at Dialog Ablation 2020. We took part in the taxonomy enrichment task. So, taxonomies are three structures that organize terms in a semantic hierarchy. So taxonomy relations are hypernymy relations or is-a relations. For example, bird is an animal and banana is a fruit and so on. So the goal of the taxonomy enrichment task was to extend an existing taxonomy through WordNet with relations to new unseen words. So specifically, given taxonomy T, where each node is a set of phrases representing a word sense, this set of phrases is also called synset. And each edge connects synset having hypernym relation. For a new unseen word, W predict its hypernym synset in the taxonomy. So let's see an example. For example, here on the right side, it's a taxonomy, and we get a new unseen word and want to predict its position in their taxonomy graph. So true for first order hypernym of marmelade is кондитерское изделие. But кондитерское изделие also has its own hypernyms of сладкое сладости and продукты питания. And the metric for this challenge treats all three synsets сладкое сладости, продукты питания, кондитерское изделие as true predictions for their input word marmelade. So organizers provide the following data. They provide pairs of word and its hypernym synsets in the existing taxonomy WordNet. Also, they provide a lot of corpora containing new unseen words that we need predictions for. So, for example, for the word marmelade, we can find a lot of context sentences with their mentioned marmelade in this corpora. So we can a little bit reformulate the task maybe. So for a given input word W, having set of its context in a corpora, so we have context C, the task is to predict its hypernym synsets. Okay, so we're trying to solve this task using the BERT architecture. So BERT is a bidirectional encoder of the original transformer by Vaswani et al. And it was trained on math language modeling objective plus next sentence prediction loss function. Particularly the BERT that we used is called RuBERT, and it's actually a multilingual BERT by Google with resampled vocabulary for Russian language and fine-tuned on Russian Wikipedia and news. So BERT provides very rich contextualized representations for the input texts. So how do we try to solve the task? First, we tried two approaches, unsupervised approach and supervised approach. So if we want to solve it in the unsupervised fashion, then we do not want to train on any labeled data right now. Okay, let's try to use BERT in a supervised session. The architecture is the following. So in short, we independently encode input word using BERT, taxonomy phrases using BERT, and then we use the cosine scoring function to score each pair of word taxonomy phrase, and perform simple nearest neighbor search and nearest neighbor classifier to predict which taxonomy phrases are actual hypernyms for the input word. So if we to describe it step by step, first we encode input word V as average of its contexts. So here you can see that we're averaging over all contexts, and here it's a representation of the context. So how do we get it? So we take context with the word as an input to T transformer, or HyBERT in our case. Then we take output representations of transformer and use some reduce function over representations of subtokens to get one vector for one context. Then to encode taxonomy phrase from the taxonomy, we so as you remember, hypernym synsets for the word actually are set of phrases. That's why if we score each word with each phrase, then we can score synsets also. So to encode phrase from the taxonomy, we just like phrase like продукты питания, we input it to the transformer of HyBERT and just use some reduction function on top of output representations of subtokens of the input sequence. I will later say what the reduction function will be for our case. Okay, so here at this stage we get we encode input word and phrase from the taxonomy. Yeah, to be more precise, we use the following sequence as the input to BERT while representing input word. So we just use the context with the word and add special tokens of BERT on the left and on the right. And we encode taxonomy phrase, also just taking the taxonomy phrase without any context and adding special tokens. Okay, so now we encoded input word and phrase from their taxonomy, and we want to score. Actually, our goal is to score every synset in the taxonomy on the topic of whether is it a hypernym synset for the input word or not. So to represent synset, we actually just take average of its phrases representations. So each synset is just a set of phrases. We just take its average, and that's the representation. And to score the input word and current synset, we just take its cosine similarity. After that, we can calculate similarities for all the synsets in the taxonomy and rank synset according to the score. The challenge so there actually the organizers want top 10 predictions of the hypernym synset. So we just take top 10 according to the similarity. also, because of their detail, that hypernyms of true hypernyms of words are also considered true predictions, we actually are not taking the actual prediction, the exact predictions, but take hypernyms of predicted top 10 words, top 10 syntax. Okay, so that's the procedure. So here is the BERT, or the encoding of the input word. Just to say it one more time, so we take context of the word with the word and special tokens. We are split into subtokens with word piece tokenizer. Then we input it to BERT architecture and group output subtokens into 4 groups. One CLS subtoken, the next one subtokens corresponding to the input word, next subtokens corresponding to the context, and the last subtoken corresponding to CEP. Okay, so now we have different ways to get the final representation for the input word. So we have representations of subtokens. We want one vector. So the simplest approach here would be to just average all subtokens. We compare it with taking just CLS representation, taking just averaging just subtokens for the input word, averaging subtokens for the input word and context, and averaging special tokens plus subtokens corresponding to the input word. These are actually different reduction functions that were seen previously in the formula. Okay, so yeah, so these are different ways to reduce subtoken representations for the input word, but for the taxonomy phrase, we always take average of all subtokens, so we don't experiment with that. Okay, so here is the unsupervised approach. I will later present the results we got for it. Now I will explain also what we tried in the supervised fashion. So now we want to predict hypernym synthets based on the contexts of the word, but training on a data set of known word and its hypernym syntax pairs. So we know that there was a word like this and the hypernyms syntax like this. We want to train it and predict hypernym syntax for new unseed words. So how do we do that? Actually, we use the same unsupervised pipeline for HyBERT as before, but we fine-tune HyBERT using cross-entropy loss for each correct hypernym phrase in the target taxonomy. So if we write down the whole expression for each pair of word of training input word and its hypernym syntax, then it will be the loss function will look like this on the bottom of the page. As you can see, we average cross entropies over all hypernym phrases, over all correct hypernym phrases for the input word. Okay, this is the supervised approach. Now, what we have also tried, we had a hypothesis that removing the hypernym word via masking might promote model to predict hypernyms or synonyms. So what it means So for example, we have this context marmelade идет к чаю. We can replace all subtokens corresponding to marmelade, the input word, with a single special token mask. And we can inference in the unsupervised fashion or the supervised fashion in the same manner, just with the masking. We do that only, so we add masking, and we do that only to input word, not to hypernym phrase. Okay, so here are the results. Here's the final table. For 3 first rows show baseline models we compared with, and the last 2 rows represent our approaches. So as you can see, actually our unsupervised HyBERT significantly outperforms HyBERT's unsupervised baseline provided by the organizers of the challenge. Almost twice as better. Then we also compare it to the style of approach. It's a supervised approach. It uses a similar projection function method, projection function learning method to predict hypernyms, and we also perform the method. Also, we see that fine-tuning HyBERT actually helps a lot. So in the particular task, the fine-tuning of HyBERT helps in predicting hypernyms. But still, HyBERT fails to outperform the simple fast text baseline. One of our hypotheses is that HyBERT struggles to classify over a large amount of classes compared to fast text, and also we used the setting where taxonomy phrase is encoded using BERT without any context, and it's this setting is quite unnatural for HyBERT, so here might be some loss in performance. Next, a few ablation studies we did. We tried different reduction functions when we are reducing output representations for tokens corresponding to input word context. Here you can see that the simplest approach, the simplest approach is the second row, where we can just average subtokens corresponding to the whole sequence. This is the first idea that comes to mind, and it's not its performance is not that good. So as we can see, the best model averages all subtokens except subtokens for context, so we remove context from our representation, and it significantly improves the metrics. Still, of course, this representation is using the context because attention layers in BERT are using all words in the input sequence. We also experimented with adding and removing masking. So the first 2 rows correspond to unsupervised approach, and as you can see, if we add masking here, then the HyBERT drops in performance. But if we actually fine-tune HyBERT with the masking during training, so if HyBERT sees masked input words during training, then during inference it gives some improvement. So thank you a lot. Our implementation can be found on this GitHub.